baryonic mass is stuck in the middle. But most of the overall mass is out here with the galaxies, i.e. behaving like collisionless particles. So all the stuff we can see, 10% of it's out here, and then 90% of it's in here. But the mass affecting the background galaxies from weak lensing is out here. So what this is that most of the mass is not where most of the baryonic mass is. And so this tells us dark matter must exist. This is a really straight, direct detection of mass that is present, but is not where the mass we can see is not where the baryonic mass is, right? So I'd say even by the criterion of that review article from 2002, MOND is now more speculative than dark matter. Arr! All right. So we're seeing mass that's not where the baryonic mass is. There must be dark matter. Even if you think, I mean, this doesn't mean that MOND is wrong. It just means it's more speculative. But even if you modify Newton's dynamics, you still need dark matter in order to explain this observation. Even if you don't like the fact that my cosmology arguments were based on, hey, my cosmology theory explains so much, and I need dark matter to make it work, and you think that that's ad hoc, even then, you need dark matter to explain this observation. Dark matter really exists. All right, so Rudy and Moon just asked almost the same question. Dark matter does not interact with itself other than gravitationally. For the most part, that's true. It'll interact with itself probably via the weak force, but that's very infrequent. Right? So dark matter has mass, but is collisionless. And yes, and that's because basically it doesn't interact with itself, right? Except via gravity. Collision is what happens when you get strong interactions when two particles move close to each other. I don't know a lot about mirror matter, so I can't really say a whole lot. So it is going right through us, yes. There's not a lot of it. The density of dark matter is much less than the density of air, but it is still going through it. But it still has a particle nature. Yeah, so it's like neutrinos. Neutrinos do that. Here's my little comic, but I'll skip that because we're out of time. So here's my summary. Dark matter makes up most of the mass of galaxies and galaxy clusters. Something like 90% of the mass of galaxies and galaxy clusters is dark matter. It's spread diffusely throughout galaxies, but it's localized there. Right? It clumps in galaxies and it clumps in galaxy clusters. Okay? It cannot be made up of normal stuff, protons and neutrons. We have a few lines of argument for that. The early universe element formation tells us we don't have enough protons and neutrons. Also, we saw in the bullet cluster that it's got to be non-baryonic. It doesn't interact with light at all, only interacts weakly via gravity. Well, this is slightly wrong in that it actually interacts with light via gravity. Okay, fine. But it does not interact directly with light. It doesn't emit or absorb light. It only interacts with light via gravity. And that's how it interacts with everything else. And it has been detected multiple ways, and this is really the key thing here. Multiple different ways we've detected dark matter from the effect of its gravity. Right? Cosmology models, kinematics of galaxy clusters, structure formation in cosmology. Interacting clusters where we see the gravitational lensing shows us the dark matter is not where the baryonic matter is. Multiple different ways. We have detected the effect of its gravity. We have seen there has to be something there doing gravity that's not baryonic. And it's real. We cannot explain all of the observations anymore just by modifying our theory of gravity. And so that's the end, that's the summary. So yeah, so well, 85%, 90, 95%. Yeah, something like 85% of matter. Well, so here's the numbers. 5% of the energy density of the universe is normal matter, and 25% is dark matter, something like that. Right, so about 5/6, more or less, of the mass, of the regular mass is dark matter, as opposed to dark energy. Right, so the positron, yes, so that's still not confirmed. I'd say that's sort of speculative. Does dark matter exist between galaxies? Yes, although it is lower density there than it is inside a galaxy. So if you look at our galaxy and the Andromeda galaxy, the dark matter halos, so the Andromeda galaxy is about, 3 million light years away, something like that. And each galaxy is about 100,000 light years across. All right, so the ratio of the distance between them to their size is like 30-to-1. So it's like take 2 quarters and put them a meter apart. That's a little model of us in the Andromeda galaxies. Our dark matter halos extend out a factor of 10 times farther than the stars do, so their dark matter halos actually overlap. So yes, dark matter exists between galaxies, but it's concentrated in the galaxies and in the galaxy clusters. If you look at the big cosmic voids, there's a little bit of dark matter even there, but it's a whole lot less than there is in the clusters of galaxies. So it's clumped in galaxies, but it's much more diffuse than the stars and the gas. Right? So think of a big kind of halo, and when I say halo, don't think of a round ring, but think of what happens when you have a lot of salt water in your eyes and you look at a light and you see a big glow around it. That's a big halo. Think of that as the dark matter, and then the light bulb right at the center is the stars and the gas. That's kind of how galaxies are. All right, other questions? And I know I missed some questions early on, so feel free to ask them again right now. Yeah, so dark matter and the density of dark matter in the room where you are is very low. We're in a very high density normal matter stuff. So it's extremely low, but yeah, there's dark matter occasionally going through you. Oh, good. And Bao found the dark matter wrap. Do we have any idea about the probable direction of velocity of the dark matter particles? Yes, every direction. So the dark matter halo as a whole is at rest with respect to our galaxy. So they're going in every which direction. The velocities we know have to be, the velocities are probably high because they're particles, but they have to be low so that the kinetic energy, and I'll go ahead and say 1/2 mv squared, where v is the velocity and m is the mass. Their kinetic energy has to be a whole lot less than mc squared. That's what we call cold dark matter. Cold dark matter means dark matter whose average velocities are non-relativistic, right? To make all the cosmology models work and everything else, we need cold dark matter. So dark matter velocities, it'll depend on what their masses are, but their velocities are such that their kinetic energy is a whole lot less than their mass energy. Found a large clump of dark matter near Earth. I'm not sure about that. Dark matter does clump, it turns out, on sizes even smaller than galaxies. You can find some sub-halo concentrations of dark matter, but again, remember that the clumping is going to be on scales of at least hundreds and probably thousands of light years. It's not clumping on star or planet or solar system sizes. If neutrons are affected by magnetic fields, why can't they be contained in a magnetic vessel for nuclear fusion? Because they're not nearly as strongly affected as charged particles are, right? So they're affected by magnetic fields, but a proton is affected a whole lot more. Does dark matter exist in the center of the Earth or the center of the Sun? Yes, but it exists in the center of the Earth in basically the same concentration as it does at the surface of the Earth, right? A little bit more, but not much. So the gravity well of the Earth is not big enough to really collect dark matter. The same with the Sun, all right? So it's spread uniformly and permeates through all of it. So basically it's at the center of the Sun. Yeah, it's the same as what's going through Moon and everybody else too. Could the clumping account for the Kobe data anisotropy? Are you talking about the low order data anisotropy? I actually haven't kept up with that, and I'm not sure what current thinking is about the lowest order Kobe data anisotropy, and maybe a dark matter subhalo clump could do it. I'm not sure. Yes, so the dark matter clump, well, okay, that's saying it a little backwards, though. They are gravitationally bound to the galaxies, yes, but most of the mass of the galaxies is dark matter, right? So they're gravitationally bound to themselves. It's not really right to say that it's gravitationally bound to the galaxy if you're talking about all the stars in the galaxy. It's mostly dark matter. So it's mostly the dark matter that is keeping all the stars gravitationally bound to the galaxy. So yes, so the velocities have to be low enough to allow them to clump, but they have to be high enough that they don't clump even more. Right? So you can set some limits on that, and I can't actually tell you what those limits are because I don't know. But it's about the same as the stars. No, it's probably faster than the stars because it's spread out farther than the stars, right? The dark matter halos are spread out 10 times the size of the stars and the gas. So you're going to expect velocities that are higher than the velocities of the stars as a result of that. Any other questions? All right, here's a long question. Could there be some kind of intermediate stuff between regular matter and energy? Could the gravitational properties attributed to dark matter be an effect of the constant change between matter and energy, the interconversions that are going on all the time, not really stuff, but an effect? Why are we calling it matter when it seems so little like matter? Does dark matter seem to clump in any way that relates to matter to energy conversions? That's highly speculative. I'm not sure. I'm not even sure exactly what it would mean to say something intermediate between matter and energy. Matter is a form of energy, and when I say matter, what I mean is something with mass. And a particle either has mass or it doesn't. It can have a very low mass. So if you have, if you have a particle that has low mass and is moving fast enough that its radiation, that its velocity is, or its kinetic energy is much higher than its mass energy, right? So it's moving very close to the speed of light. It behaves more like radiation than like matter. So in fact, in the very early universe, very, very early universe, we can treat electrons as massless. Why? Because their kinetic energy is so much higher than their mass energy. So when I say matter, what I really mean is something that has mass, but even more than that, it means something that has mass that matters, right? Mass that's significant. So is there something intermediate between mass and radiation? I'm not really sure what that would mean. There's a black hole at the center of the galaxy, and the sun is not at the center. Does the sun move around the black hole, and does dark matter keep the sun locked in place so that it does not enter the black hole's event horizon? There is a black hole at the center of our galaxy, but the mass of it is tiny compared to the mass of our galaxy. So the overall mass of our galaxy is, are you ready for this, 10 to the 12 solar masses, which is 1,000,000 billion solar masses, I think, something like that. Whereas the mass of the black hole is only a few million solar masses. So it's a supermassive black hole. It's huge, it's scary, but it's tiny compared to the galaxy as a whole. So when it comes to the dynamics of stuff like the sun, far from the center of the black hole is irrelevant. All right, it's not black hole's gravity is a whole lot less than the gravity of all the stars between us and the center of the galaxy, and it's a whole lot less than the mass of all the dark matter. So there is a supermassive black hole there, but this far from it, its gravity is just gravity, and it's very small compared to anything else. So there's no worry about the black hole at the center of our galaxy. There's no worry about falling in or not. It's just because we're moving fast enough that we stay in a circular orbit that is 20,000 light years from the center of the galaxy. That's what keeps us from falling into the center of the galaxy. So it's not dark matter per se, although we do need dark matter to explain our velocity, but without dark matter, we go winging off into intergalactic space. So in fact, the dark matter is holding us closer to that black hole. So we're not orbiting the black hole. We're not orbiting the black hole. We're orbiting the center of the galaxy. The black hole happens to be at the place that we're orbiting, but it's not the black hole's gravity that's holding us in. So the density is low within the Earth and the Sun because dark matter doesn't interact collide. So it blows right through the center of mass of the Earth and the Sun. It just keeps going rather than splats to a stop. Exactly. That's exactly right. Neutrinos do the same thing. There's this great Isaac Asimov quote that he said, "To a neutrino, matter is just a high grade of vacuum." Why is the black hole there? Well, that's actually a pretty hard question that that a lot of people are working hard on right now, but ultimately it comes from the fact that it is the center gravity well of the galaxy. It's the place where most mass concentrates, and so enough mass concentrated there to form a black hole. Now there's sort of we don't know, do galaxies form first or do black holes form first? Where do the first black holes come from? Where do the first stars come from? We have some ideas about that, and we're starting to get data on that, but that's an active field in astronomy research right now. Is the rate of dark matter infall into the black hole significantly greater than the rate of Hawking radiation so that the black hole will not evaporate until it's captured nearly all the dark matter? Don't know. The problem is dark matter infall to the black hole rate is very small because most of the dark matter is spread out. It's going to take many times the age of the universe to significantly increase the mass of black holes by sucking up dark matter. Right? There's so much more dark matter than black holes that it will take a long time for the dark matter to move through the universe and capture all that, or make time for the black holes to move through the universe and capture all that dark matter. So honestly, I'm not sure how the timescale of that compares to the Hawking radiation timescale. So I'm not really sure. Doesn't dark matter sound an awful lot like